Good morning, good afternoon, or good evening, everyone. I'm Ko Yenze, and today I'll be presenting a breakthrough innovation in sustainable space engineering, LignoSat, the world's first wooden satellite. As space activity increases, so does space debris and atmospheric pollution from burning satellites. Traditional satellites re-entering Earth's atmosphere release harmful metallic particles which accumulate in the upper atmosphere. To address this, scientists in Japan created LignoSat, which is a satellite made primarily out of magnolia wood. It was launched from the International Space Station in 2024, which is last year. Its goal is to test whether wood can survive harsh space conditions and whether it can burn up safely without releasing toxic debris. Now let's move on to the physics mechanism. As you can see here, I've calculated the volume and areas, orbital speed and period, gravity and gravitational force, and so on and so forth. But let me elaborate slightly regarding the physics concepts involved in this innovation. First, we have thermal expansion and contraction. In its orbit, LignoSat experiences drastic temperature changes from about 120 degrees Celsius in sunlight to negative 100 Celsius in shadow. These fluctuations cause materials, including wood, to expand and contract, testing how wood maintains its structural integrity. The strain sensors in LignoSat measure this expansion and contraction, which is a practical application of thermal physics. Next, we have radiation interaction with matter. Following up is electromagnetic interference, which is also known as EMI. Since wood is non-conductive, it doesn't shield against electromagnetic fields like metal does. LignoSat helps study how Earth's geomagnetic field affects communication system by applying the concept of electromagnetic induction and field penetration. We also have heat transfer involving conduction, convection, and radiation. In space, heat transfer occurs mainly through radiation since there's no air for convection. LignoSat's temperature sensors measure how heat radiates through wood, giving insight into thermal conductivity and emissivity of natural materials. Without further ado, let's move on to the first key concept, which is development. LignoSat is the first satellite built within wooden exterior panels. The panels were assembled using traditional Japanese joinery, as you can see here, meaning no screws, glue, or metal fasteners. This prevents outgassing and reduces mass, while also honoring cultural craftsmanship. Magnolia wood was selected due to its strength, its low shrinking rate, and high dimensional stability in vacuum and temperature changes, which are important physics properties for orbital structures. This development stage highlights how science connects with culture and history, and how traditional knowledge can support modern engineering. Next, to properly evaluate whether wood can function as a reliable space material, LignoSat was equipped with multiple onboard sensors to detect, firstly, structural strain. Strain sensors were installed to measure how the wooden panels expand, contract, or flex. Next, to detect and monitor temperature cycles. The sensors help determine how heat distributes through the wooden body, whether internal electronics remain within safe operating ranges, and how wood's insulating ability affects radiation, heating, and cooling cycles. Next, to also monitor radiation levels. LignoSat carries radiation sensors to measure ionizing radiation, including charged particles from solar activity and cosmic rays. By tracking radiation exposure and comparing it with wood surface wear, scientists can engineer protective coatings and treatments for future eco-friendly spacecraft materials. Next, to also monitor geomagnetic interference. LignoSat also tracks Earth magnetic fields to see whether it interferes with the satellite systems. Wooden satellites have less natural shielding than metal ones, so electronics may be more exposed to magnetic interference. Regarding the development contributions, first of all, we have promoting sustainable material use in space tech. Conventional satellites release metallic dust when they burn up, such as aluminum and titanium particles that linger in the atmosphere. Wood, however, is biodegradable, it is renewable, and it evaporates cleanly. This means lower environmental impact and reduced orbital debris, supporting global sustainability goals. The second point is advancement in monitoring systems. By testing electromagnetic effects on a non-metallic satellite body, LignoSat helps engineers to explore new signal shielding methods, non-metal satellite structures, and also border material choices for future spacecraft. The second key concept that I would like to highlight on is application. One of the most important outcomes of LignOSat mission is how its data can be applied to improve real-world technology, both on Earth and in future space missions. Because the satellite is made of wood, it allows scientists to observe nanoscale degradation pathways, meaning they can see exactly how tiny cracks, fiber break down, and microscopic defects form when exposed to radiation, vacuum, and extreme temperature changes in space. It helps scientists and material engineers design better protective coatings and surface treatments. These coatings can then be used not just for satellites, but also in industries where materials face harsh conditions here on Earth. For example, buildings in tropical or coastal areas face strong UV rays, humidity, and salt corrosion. By understanding how natural materials deteriorate in orbit, far harsher environment, chemists can develop non-toxic, long-lasting protective finishes for sustainable building facades and timber architecture. LignOSat also tests low-power communication, meaning it sends signals using very little energy. This shows that even a small and lightweight satellite can still share information from space without needing large batteries or big antennas. Because it uses a wooden body, scientists can also see how radio signals work without metal around them. This is useful for future small satellites, especially those made by schools or universities, because it makes space communication cheaper, more energy efficient, and more environmentally friendly. This application contributes to the society and environment in terms of faster development of high durability and low toxicity wood coatings. Aside from that, it is also a proof of concept for ultra-low power, small form factor links. Small satellites with low power and simple antennas can still operate efficiently in orbit. This supports global research and democratics access to space, especially for student missions. However, with the application, there also must be the limitations of LignOSat. The mission lasted around 10 months, which is too short to predict multi-year durability. It is not representative of lunar or Martian conditions, so we still do not know whether wood can withstand long-term radiation, thus abrasion or cosmic rays. Another limitation is geomagnetic and structural tolerance issues. NASA observed potential interference from Earth's magnetic field. Also, wood can subtly shrink in vacuum. Even 0.1 millimeter movement can disrupt antennas or wiring. This means that engineering tolerance must be extremely precise. First of all, the impact of those limitations that I've mentioned earlier can cause an incomplete durability data for long-term missions. More missions and simulations are necessary before wooden structures can be used for lunar-based construction, long-duration satellites, and also deep space probes. It is promising, but not yet fully proven. The next point is communication reliability concerns. If electromagnetic interference occurs, communication results may be inconsistent. Data from amateur radio trials may be incomplete or inaccurate. This limits the reliability of radio experiments and means more testing is needed before real-world implementation. For communication and collaboration, there's this table here where you can clearly see which organization plays what key role and what are the contributions they bring to the innovation of LignOSat. The LignOSat mission shows how different organizations work together to make this project possible. For example, Kyoto University led the research and designed the satellite scientific systems. Sumitomo Forestry provided their knowledge about wood and used traditional joinery methods to build the wooden structure without metal parts. JAXA supported the mission by handling the launch and operation through the Kibo module on the ISS, and NASA helped release the satellite into orbit. Throughout the process, these teams communicated closely, they shared resources, and combined their skills to test the wood, install sensors, and make sure that the satellite was safe in space. This mission proves that successful space projects depend on how strong teamwork, shared knowledge, and international collaboration. The contributions of the communication and collaboration points that I've elaborated in the previous slide, includes, first of all, material innovation, traditional joinery, aerospace physics, and also new knowledge of natural structural materials under extreme environments. Scientific advancement would also be the next point that I would like to highlight on. First ever real orbital data on wood behavior allows better understanding of nanoscale degradation and coating development. Operational capability is also another point under contribution of communication and collaboration. It meets ISS safety requirements and proves a non-metal satellite can function in orbit, influencing future sustainable satellite policies. Last but not least is the Shiki concept of influence. Lignosat encourages the idea that if wood can survive space, we may one day use renewable materials for satellite shells, habitat structures, and planetary research posts. This mission shifts public mindset, industry direction, and policy toward eco-friendly aerospace practices. It creates awareness, inspires new education pathways, and encourages sustainable engineering across nations. Therefore, in conclusion, Lignosat demonstrates how science, engineering, tradition, and environmental ethics can work together. It proves that innovative and sustainable materials like wood have real potential in modern space technology. Although further testing is still needed, Lignosat still represents a powerful step towards sustainable space exploration while showing that advanced technology can still respect our planet. That's all from me for today. Thank you very much for listening.